Okay, welcome back. We'll finish our discussion on Burrows Wheeler indexes in this lecture. So as a recap, in the last couple of lectures, we understood what Burrows Wheeler transform is. So given a text, Burrows Wheeler transform is nothing but you take all the cyclic rotations of the text, you sort them lexicographically, and the last column of the rotations will give you the Burrows Wheeler transform text. Right. So this is a simple definition. We also saw why is Burrows Wheeler transform useful for compression. So we saw various examples, including this example shown here, where the compression comes from the fact that once we compute Burrows Wheeler transform, equal letters tend to come together, and because of this property we can use run length encoding to reduce the space needed to represent a particular text. We also saw that given Burrows Wheeler transform, we can go back to the original text. So this is a lossless compression, because given the Burrows Wheeler transform, we saw an algorithm that gives us the original text back. This was done using concept of L and F columns, and using a mapping between these two columns, which we refer to as LF mapping, we were able to reconstruct the original text back from Burrows Wheeler transform text T. Right. So this was the concept that we were using, that given columns, we used columns F and L, and in a backward fashion we reconstructed the text T using a mapping between L and F columns. So before we proceed further, I want to make two remarks. If you look at all the data compression techniques, Burrows Wheeler transform stands alone in that world because it is very different from all other compression algorithms. For example, Huffman encoding, arithmetic encoding, Lempel-Ziv, these are some of the well known compression techniques, and Burrows Wheeler transform is very unique in some sense, because, and it's also not as intuitive, because knowing the fact that using the last column will be compressible and will also be invertible to the original text is not very intuitive. So given this unique nature of this algorithm, one can wonder, like, how did the authors invent this technique? How did they stumble upon this idea? So for this, if you are curious, you can go and watch an interview of one of the authors. So in this interview, they give an intuition of how they stumbled upon this idea. It turned out that Michael Burrows' advisor, David Wheeler, he discovered this idea while he was working on data compression at Bell Labs in 1983. But when he came upon this idea, his initial impression was that this idea will not be practical, because at the time computers were very slow, and he thought that using this algorithm will be extremely slow compared to the other known techniques. But much later in 1994, his student Michael Burrows convinced him that this idea is practical, and they together published this idea in 1994. So in this case, David Wheeler, the way this idea came to him was when he was trying to build a compression algorithm, and he was trying to see whether the sorted context of the characters can be used to encode the text. So he was trying to see whether sorting the context around the characters can be useful for compression or not. And at that point they stumbled upon this Burrows Wheeler transform technique, and they published it in 1994. So you can watch the YouTube video for more if you want to learn more. Another remark I want to make is that the compression efficiency of Burrows Wheeler transform is clearly governed by the number of runs of repeated characters in the transform. So for example, in this example we saw the number of runs, equal letter runs, is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 blocks of equal letter characters, or equivalently I can say that 8 runs of equal letter characters. So, this technique works well in practice, but it was open for a long time. Why? Theoretically it works well. So, a theoretical justification of this technique was lacking for many years. Very recently, a known trivial upper bound on the number of runs in the Burrows Wheeler transform was mathematically proven in 2022. So, this publication is in 2022, and for those of you who want to learn more about what that upper bound is and how it was derived, they can refer to this paper. So, this was a very recent result, it came much later after the discovery of Burrows Wheeler transform. So, it in some sense it sheds light on why Burrows Wheeler transform works so well in practice, especially for biological sequencing data. Okay. So, now that these two remarks are made, we are back to our original topic of Burrows Wheeler index. Our original motivation of Burrows Wheeler index was to achieve a space efficient index of large genomics texts. For example, if we considered as an example of large genome of Australian lungfish whose length is 43 billion base pair long. In those cases, we saw that the input text only requires 11 GB space, but if we use suffix arrays and suffix trees, even though asymptotically they require linear space, but if we look at the exact number of bit counts that they need, then the space requirement increases quickly because of the constants involved. So, for example, in case of DNA, this value is small because in case of DNA the alphabet size is only 4. So, for each character I only need 2 bits to store each character of the genome, whereas in case of suffix array and suffix tree the space requirements are significantly more, and even for longer genomes this can be computationally prohibitive. So, in this topic we have been looking for a space efficient index that can support the functionality of suffix arrays and suffix trees, but maybe require much less space than these indexes. So, let us look at and finish our discussion of Burrows Wheeler index, which is a space efficient version of suffix arrays and suffix trees. So far we have already addressed what is Burrows Wheeler transform, why is Burrows Wheeler transform useful for compression, and given Burrows Wheeler text how we get the original text back. But these questions are not enough to understand why this compression technique is useful for indexing as well, because an index must support fast information retrieval as well, right. So, we will see now how Burrows Wheeler transform is useful for fast pattern matching and fast information retrieval as well. So, in a Burrows Wheeler transform based index, we will store the Burrows Wheeler transform of the text T. So, for example, if my text T is A B A B A dollar, then the last column gives me the Burrows Wheeler transform text. So, I am going to store this Burrows Wheeler transform text in my index. Next, I am going to store an array that has sigma integers. So, for example, in this particular example I will store an array which has 3 values, and these values will just convey the boundaries of these blocks. So, there are 3 blocks in this F column, because remember that F column has a very simple structure. It will have a dollar symbol followed by a few A characters followed by a few B characters, because we had lexicographically sorted all cyclic rotations, and F column represents the first column of that matrix. So, therefore, it will follow a simple structure, and I am only keeping an array that stores the boundaries of those equal letter blocks. right. So, this will be in this case 0, 1 and 5. So, these are the values that I am storing to mark these boundaries of equal letter blocks. I do not need to store the column F explicitly. So, storing these boundary values is enough. For example, these boundary values, if I want to quickly know which row starts with the second occurrence of B character, then I can immediately tell this in order 1 time, because I have access to the offset where character B characters start, right, and then I just need to add 2 above that. So, the offset where the B characters start and then plus 2 will immediately give me the row number where B2 starts. So, access to column F and knowing any row of a character can be done in order 1 time by just having this small array of sigma integers. Now, the third part and the final part of the Burrows Wheeler Transform Index will be a succinct ranked data structure on BWT. So, on this Burrows Wheeler transform text, I am also going to support a ranked data structure. Now, remember that we had discussed succinct ranked data structures in our introduction module. Let us revisit that discussion. So, in our introduction module, we had discussed the rank operations on bit vector. So, in that case, basically if we are given a bit vector B, then a query can be made at position I, and it should immediately tell me what is the count of ones until offset I. That is, I should be able to immediately answer what is the number of 1 characters or what is the number of 1 symbols in the interval 1 to I. So, as an example on the right, if I make this query at position 6, then I should get a value 3, because there are 3 occurrences of 1 character until now. So, for supporting these type of queries, we had discussed a succinct index that is able to respond to each query in order 1 time, and the index size was very small. So, in terms of the number of bits, it required only n plus small o n space, right. So, but this is for bit vectors. In our case, we need a ranks query support for bigger alphabet. So, this is not a bit vector anymore. Here we have a vector of values coming from alphabet sigma. So, we can generalize these rank operations for larger alphabet as well. So, now suppose if I am given a text T over alphabet sigma, I can similarly ask rank queries of type, for example, until position I, what is the number of A characters occurring in that interval. So, for example, I can make a rank query here asking what is the number of A characters until this position, and the answer should be 2, because this is 1 occurrence and this is the second occurrence. So, similarly, I can make a rank query of character C, character G or character T at any position I in this vector. Now, how do we address or how do we extend our previous solution that was defined on bit vectors to a solution that is defined on a vector of containing characters of larger alphabet? Well, one simple way of doing that would be to convert the original text to multiple bit vectors. For example, if my text is composed of sigma A T C G, then I can split my text into 4 bit vectors, each specifying, for example, in this case the first bit vector corresponding to symbol A will specify 1 wherever 1A occurs, or 0 wherever any other character occurs, right. So, in this case 1 will represent occurrence of A symbol. Similarly, in bit vector corresponding to symbol C, 1 will occur corresponding to occurrence of C characters and so on. Now I can support rank queries in the original way, because I have access to 4 bit vectors. I can extend the same idea on these 4 bit vectors and I can respond to the rank queries. For example, if I want to respond to the rank A query, then I can use the rank data structure on bit vector A. Similarly, for rank query of C character, then I can make a rank query on bit vector C and so on. Well, in this case, observe that if we want to analyze this particular solution, we are building sigma bit vectors and we are applying our previous solution to each of these bit vectors. So, therefore, the index size will be sigma times n plus small o n, right, because we are using sigma number of rank data structures, and in each case the access time remains order 1, because for in our previous case the access time was order 1. Similarly, now our access time is order 1, because all we need to do is for any rank query we can go to that bit vector and make a order 1 answer. So, this is one way, but it turns out there is a more space efficient way in the literature as well, and that is known as wavelet tree data structure. In that case, if we use wavelet tree data structure, then the rank queries can be supported in less space. So, in this case the index space is only n log sigma 1 plus small o 1 bits. So, this is reduced from n sigma 1 plus small o 1 bits. So, observe that I can equivalently write this as n sigma 1 plus small o 1 bits, and in this case it is the sigma factor has reduced to log sigma. So, this one is more space efficient, but here the access time is increased from order 1 to order log sigma, that is each rank query will take order log sigma time. So, this data structure we have not covered as part of this course, but we will be using this as a result in the later slides. So, the key point to remember is that each rank query requires order log sigma time using this index known as wavelet tree. So, now with this rank data structure support, let us come back to the Burrows Wheeler index. So, we had 3 ingredients of the Burrows Wheeler index, as I mentioned before. One is the Burrows Wheeler transform text, second is the array specifying these boundaries of equal letter runs in column F, and third is the succinct rank data structure on the Burrows Wheeler transform text T. Well, observe that now the overall index takes very small amount of space, because if I want to store the Burrows Wheeler transform, I only need n log sigma bits, because these are just n symbols from alphabet sigma. So, for that if I want to save it, I only need an array which occupies n log sigma bits. For the second part, I only need a very small array which has sigma integers. So, for example, if I am talking about DNA sequence, all I am requiring is an array of size 4, right. So, this is going to be negligible, because for small alphabets like English text or DNA sequence, the alphabet size is usually very small, and in that case this is a very small array and we can even ignore its size to the overall size contribution. Third is the succinct data structure, for which we are using wavelet trees, and we already saw in the previous slide that the wavelet trees are going to use this much space, that is n log sigma 1 plus small o 1 bits. So, overall so far the Burrows Wheeler transform index has occupied very small amount of space. So, this particular factors are smaller, and this is probably the major contributing part, and you can already see that this is much smaller than what suffix arrays and suffix trees were occupying. So, in suffix arrays and suffix trees the space requirement was n log n or more, whereas now the space requirement is only n log sigma. So, we are working with a very small index now, and I want to convince you that this small index is powerful to answer important pattern matching queries. So, first query that we are going to answer using this Burrows Wheeler Transform Index is, given a Burrows Wheeler Transform Index of text T and you are given a pattern P, calculate the number of occurrences of P in T. So, for this, for counting the number of occurrences of pattern P in text T, remember that when we were doing binary searches, we were able to do, so when we had suffix array, we were able to do binary searches, right. So, for pattern ABA, all I could do is I needed a binary search of character A, then I narrowed down my search range, then I did a binary search of character B, and then I did a binary search of character A. So, in suffix array it was very easy, that all I needed was a binary search because the suffixes were sorted in lexicographical order. But with Burrows Wheeler Transform Index we have to be more careful, because we do not have access to these middle columns here. That means we do not have access to the suffixes that we had in suffix array. So, we need a slightly different strategy here to work it out. The strategy will work as following: we will search our pattern in the reverse order in a backward manner. So, we will start searching for character A first. So, from our small array where we store the boundary offsets, we can immediately find out the rows which correspond to character A's. So, we can immediately find out which rows start from character A onwards, right. So, this was from the array of sigma integers, and that will immediately give you access to the rows in the matrix which start from character A onwards. So, from there we know that we have to look at this interval, because these characters precede characters A, right, and our next character in the pattern P in the reverse order is P. So, we have to look for character B now. Now one naive way of doing that would be to do a linear scan, but we do not want to do that because that would be a bad way of searching. What we can do is we can make use of rank data structure, and we can do a rank query here. So, we can do a rank query of character B, that is what we are interested in, and we can immediately know that how many characters of B occur until this point and how many B characters occur until this point. So, the rank queries will tell us, okay, that there are 0 characters occurring above and there are 2 B characters occurring above. What that tells us is that B1 and B2 precede A's in this range. So, the first B character and the second B character are preceding characters A in this range, right. So, from there we can move one step back in the pattern and move to the next character, which is B. And again repeating the same procedure, we can ask what are the rows which correspond to B1 and B2. Using again the same logic, we will get access to the rows corresponding to B1 and B2, and again we can move to the previous character and make a rank query of A, asking how many A characters occur in until here and how many A characters occur until here. So, again from there we can know that A3 and A4 precede these B characters, and we can switch between F and L columns this way. So, because there are only 3 characters in the pattern, in this case we have finished our search and we can immediately report to the user that there are 2 occurrences of the pattern in the text. So, as far as counting is concerned, we can immediately report that we have 2 occurrences of pattern in the text. What about runtime? Well, observe that for each character in the pattern we are making 2 rank queries in column L, and we identify the range of rows in column F. So, identifying the range of rows is easily done in order 1 time, but each rank query takes order log sigma time using wavelet trees. So, therefore, because each rank query takes order log sigma time, we are spending order p log sigma time total to count occurrences of pattern P in text T. So, this gives you a flavor of how Burrows Wheeler Transform Index is giving you fast support of pattern matching, so that you can count occurrences of pattern in large text T in only p log sigma time. So, this is already very similar to what suffix trees are capable of. So, remember that suffix trees were also allowing you to do this in order p time, whereas Burrows Wheeler Transform can give you answer in p log sigma, and log sigma is a very small overhead to pay. So, in some sense Burrows Wheeler Transform Index uses small amount of space, and it can give you the functionality of what suffix arrays and suffix trees can do. Let us also try to ask a more involved problem, slightly more involved problem, in which case we also want to report all starting positions of the pattern in text T. So far in the previous problem we only reported the number of occurrences. We did not report the starting positions where the pattern occurs. So, let us also see how Burrows Wheeler Transform Index can be used to even report the starting position of the pattern as well. Now, when we were working with suffix arrays, it was very obvious that because the suffix arrays were storing the starting positions of the suffixes, we immediately got access to the positions of the pattern as well. So, for example, if you know that your pattern occurs in this range, then suffix array immediately tells you that 3 and 0 are the locations where your pattern matches, right. Whereas we do not have access to the starting locations of these suffixes in the Burrows Wheeler Transform Index, right. So, we are not storing these numbers in Burrows Wheeler Transform Index, and that is the point of optimizing space, because if we store all these numbers, then we are back to our original problem that we will be using too much space, and that is not what we want. We want to have an index that uses small amount of space. So, how do we do that? So far in the counting process we know that these are the 2 rows which correspond to our pattern hit, but we do not know where these suffixes start in the original text. How can we recover that information? Well, the key idea that we are going to use is something known as Succinct Suffix Array, in which we are going to sample a few values of suffix array and we are not going to store all values. So, for example, if my sampling rate is r, then I am going to store the suffix array values only for suffixes starting from every rth position. So, every rth character, for example, if the r is equal to 10, then I will store the suffixes starting at position 1, at position 11th, at position 21st, position 31st, and so on. So, I am going to store in some sense a sparse version of suffix arrays. So, if my sampling rate is r, then I am going to store only n by r values of suffix array. And I am going to use these sparse values in order to locate my pattern as well. Observe that if I am only storing n by r values of suffix array, I only need n by r times log n bits. So, in case of suffix array, it used n log n bits, because each number requires log n bits to store, but because I am sampling every rth value, I am going to need only n by r log n bits. and the way in the actual implementation, the way to store it would be to save it contiguously. So, for example, I can save it in a new array 6204, which is a smaller array of size n by r, and I can maintain a bit vector of size n which tells me where these values are occurring. So, using again the idea of rank data structure, I can access these values in a space efficient way that will only require n by r log n bits to store this sparse version of suffix array. Now, with this I have access to the starting locations of some of the suffixes, not all, but for some suffixes I know their starting locations. For example, I know that suffix $BA starts at position 4 in the text, but for suffix $BAA I do not know its location. So, only for some suffixes I know their starting locations, okay, but that may be enough. So, let us see. So, suppose I reach in my pattern matching, I reach this row and I know that my pattern occurs at corresponding to this row. So, now because I have access to the value of this suffix array, I can immediately know that this particular suffix starting from this location occurs at position 2 in my text T. So, for this one I am safe, I can immediately in order one time I can know the location of my string in text T. However, what if I am at this row? At this row, if my pattern is matching, how do I tell its location in the text T? Well, the trick here is that even if I do not know the location of this suffix, I can still move back maybe a few characters and subsequently I will find a suffix whose location is known. So, for example, in this case I can move back one character and I will find a suffix whose location I have already saved in my succinct suffix array. So, in this case I will move one position back, and the way to move one position back in Burrows Wheeler transform is to use LF mapping. So, I will move to the preceding character, I will make a rank query, and from there I know that I have to go to the row corresponding to symbol A2, and from there here I will find that this particular suffix starts at position 2 in the text T. So, if this suffix starts at position 2, then my original suffix must be starting at position 3 because I moved back one character. Now, if the sampling rate is r, in the worst case I may need to move back r minus 1 characters in the worst case. So, if your sampling rate is r, then I may need to move back r minus 1 characters back, and in each iteration I will need to make one rank query to jump between L and F columns. So, we can summarize this as a lemma that the Burrows Wheeler Transform Index and Succinct Suffix Array of text T takes n log sigma 1 plus small o 1 space for the Burrows Wheeler Transform Index and an additional n by r log n bits of space for the Succinct Suffix Array, where r is the sampling rate, and r really represents the time and space trade off, because if you reduce the value of r, the space requirement will reduce, but the time may go up because the backward steps may increase. But if you use a larger value of r, then if you use a dense suffix array, that is if you use a small value of r, then your space requirement will increase. So, now with this Burrows Wheeler index, it can support count operations in p log sigma time, and for any position I can also return the location of that row in the text T, that is the suffix array position I can report back in r log sigma time, because in the worst case I have to move back r minus 1 times, and in each step I need to make a rank query. So, for any index I can report its suffix array value in r log sigma time. And observe that if I make R equal to log 2 sigma by log n, then I can also offset this space required for suffix array. So, for this particular value, if I keep R to this value, then my overall requirement, space requirement, is only n log sigma bits. So, this is big O notation. But one can tweak and pick a different value of R depending on the application requirements. So, if you really need to be very fast, then you want to use a dense version of suffix array, but if you can take small runtime hit, then you can work with a sparse suffix array as well. So, as a summary, what Burrows Wheeler index is now capable of is storing the index in very small amount of space. So, for the genome length of 43 billion bases, compared to suffix array and suffix trees, Burrows Wheeler index only requires 20 GB of space, and that is already very similar to the space that you use to save the input as well. Now, this is assuming R equal to 32, that is a sampling rate of 32. So, for this particular value, it is observed that Burrows Wheeler index typically takes 0.5 bytes per character. So, this is already very close to what text is occupying, and this conveys you the power of Burrows Wheeler index and why it is so popular in many tools used today. So far we have completed our module of strings and exact matching, where we have seen algorithms where input is only known at runtime, and we have seen many algorithms such as suffix array, suffix trees, Burrows Wheeler indexes, where we can pre-process the text and do pattern matching even faster. In the next module, what we are going to do is we are going to move from exact matching to approximate matching, and that is because for many applications we need to allow some edits in terms of substitutions, insertions or deletions because of the mutations in biological sequences. So, for example, if I am comparing a human genome sequence to a rat genome sequence, they will not exactly match, there will be mutations in between those two genomes, and that is where we will need to allow some edits in the pattern matching. So, from next lecture onwards we will start module 3, which is pairwise sequence alignment. Thank you.